Angles and their measures. Way too simple for you guys, right? Okay, so we won't do that there. Now, there is some terminology I want you to be aware of so that when it's identified. Vertex obviously is going to be the angle. Initial side, when we're talking about dealing with things in trigonometry, we tend to have vertex. Our ray is going to be coming out to the right. This is going to be identified as the initial side, and the terminal side is where it stops. So it's going from some place to another place. Now we also identify rotations. This would be clockwise, counterclockwise. Now this is counterclockwise, just going once, counterclockwise going around it twice. So we can count those things. So if we take a look at it in the coordinate plane, we see this. Now you're going to see this wonderful little zero with a line going through it, little theta. When we talk about angle measures, that's generally what we're going to be using theta. If you look on your graphing calculator where your variables go in at, you've got an X, you got a T, you've got that circle with a line through it identifying theta, so it puts it in there. So, of course, you know where the quadrants are, first, second, third, and fourth, going around that way. Degrees. Now, one of the things that we're going to be talking about as we go through this is how we get to the terminal side from the initial side. We will use words like revolution. We'll go talk about a direction, clockwise. We may talk about a right angle, straight angles. We may give you the degree measure of what it is going to be. Now, I don't doubt that you can come up with these things. However, I will warn you about this right now. Draw them out with your initial side, if you need to, putting it onto Cartesian coordinate system or just a little XY grids laying down, not grids laying down, with the axes laying down. Put the initial side upon the x-axis, vertex 0, 0. From that point, if I go 45 degrees, well, that's halfway up to 90. Negative 90. This is going to give us direction. Positive is going counterclockwise. Negative is going clockwise. Yes, I understand that that does not necessarily make that much sense because they seem to be opposite each other, but these are two directions that were not identified to begin with as compatible with each other. You know, clockwise was identified with a clock, and a clock was done a long time before, or I should say in a different way than what this was. So, one of the things that you need to know is that one clockwise revolution is equal to 360 degrees. Okay. Sometimes we are going to give these things in degrees and minutes and seconds. Now, I realize that we are going to use the same terminology that we use for time. We have degrees, we have minutes, and we have seconds. So that means every degree is broken up into 60 minutes. Each and every minute is broken up into 60 seconds, just like we are dealing with time. You will be given information that's put in terms of degrees, minutes, seconds. Do not go and think that, oh, it just whatever the degrees are is point this, point that. So for example, if I'm looking down here at 15 degrees, 30 minutes. 30 minutes is what of a degree? It's half of it. That's how it goes to 15.5. So you've got to be aware of converting that stuff. So let's take a look at A here once, because that's something we do a lot of. Very temperamental. All right. So I want to go and convert that into degrees and minutes and seconds into just a plain old decimal number. So my question is, what is 6 of 60? Well, I suppose that would be 1 out of 10. So that would be like a 0.1, right? Problem is, don't start there. Don't work from right to left. Work from left to right. Work from the smallest unit on up, because then I'll show you what's going to be happening on this. So now if I've got 21 over 60, that's kind of an ugly looking number, correct? Because this is really saying 6 minutes and 21 seconds. So what I'm going to do here is 21 divided by 60, 0.35. So instead of 6 minutes, 21 seconds, this would be 6.35 minutes over 60. If you try and work your way up, it'll be a lot easier to think about than doing it the other way. So now I can just add 6 to this, divide this by 60, and I've got my next set of decimals. So that means that it's going to be for A, that would be, oops, sorry. That would be 50.1, we've got 4 decimal places, 1058 degrees. Easy enough? Got that puzzled look on your face. Oh, okay. So what happens if we've got to go back the other way? Well, that's easier than you think. 21.256 degrees. Now I've already got 21 degrees. This here is identifying the minutes, correct? So if I've got 0.256 of a minute, I take 0.256 times 60. So 0.256 times 60, and I end up with 15.36. So just like I did before, I'm going to take off the decimal point, worry about that. So now I know that I have 15 minutes. So I'm going to take that off, multiply that by 60 again, and now I end up with 21.6. But it says to the nearest second, so that means that I would have 22 seconds. Easy enough? Do a few dozen of them and it'll make sense. All right, let's take a look, see at these things. Radians. Now, this is where things start getting a little interesting. So yes, I am trying to make things really difficult for you now. We can measure circles in 3 different ways. I can do this in rotations. How many times does it go around? I can do this in degree measure. There's 360. I can also do this in radians. Radians is another form of measurement that is generally identified in the terms of pi. Okay. So, if I take a look at the information that I've got here, it says, for a circle with a radius r, central angle of theta radians, an arc. So the length of the arc is r theta. Okay. How does this actually work? So I want to find the length of an arc of a circle with radius 2 subtended by a central angle of 0.25. Okay. So radius is 2. Because theta is in radians and this formula is identified in radians, I don't really have to do much of anything except for multiply. Now, if the measure was given to us in degrees, I'd have to convert. If it was given to us in rotations, I would have to convert. But because it's given to us in radians already, it's just going to be 2 times 0.025, which means it's going to be half a meter. Now, these are going to be things that you should make sure that you have written down. 1 revolution is going to be equal to 2 pi radians. 180 degrees is equal to pi radians. 1 degree, pi over 180, 1 radian is 180 over pi. Now, when I tend to do these things, I tend to like to see them written, not so much like this, but I would write it as 1 revolution over 2 pi radians is equal to 2 pi radians over 1 revolution. I do this that way I can kind of pick and choose which one I want because things are going to be in the form of a fraction. So likewise over here, I would have 180 degrees over pi radians, which would be equal to pi, which would be equal to pi radians over 1 degrees. Those are the 2 main things that I would deal with. It's easier to set it up like that. Yeah, you got the 1 degrees pi over that. Just, for me, I've seen it work easier with this, and when students are setting it up, that seems to be a little bit easier to deal with. So, continuing on. So, if I want to convert these things from degrees to radians, by going through and having this 60 degrees, I want to get rid of the degrees. So, if I go back to what I had written down here, which one of these unit multipliers would I want to use? Would I want to use this one, first one, or the second one? Well, I'd use the second one because then that would cancel off the degree measure. So I would get this multiplied by pi over 180 degrees. So this cancels with this, and I get 3, so this is going to be equal to pi over 3. 150, same idea. Multiplied by pi over 180. This cancels off. And let's see, so if I divide this by 3's, I end up with, this goes to a 5, this goes to a 6. So this is 5 sixths, or 5 pi over 6. And you will see it written that way, where the pi is in the numerator, not next to it. So if I want negative 45, pi over 180. That goes into 184 times, so this would be negative pi over 4. Big deal. 90 degrees and 107 would be all the same kind of stuff. If you can cancel it off, you can. And now that last one there in 107 doesn't appear to be anything divisible by it, so it would just be 107 pi over 180. Do yourself a huge favor. Avoid decimals at all costs. Fractions are what this thing runs on. So I realize that they go through and put in the decimal there. That's why I bring it up. This is approximate. If you need an approximation, a ballpark number, fine. Go ahead, use the decimals. But keeping it in the form of a fraction is by far better to do. Now, you'll go through, and I definitely suggest you read through this. You've got a pi key on there, 3.14. It has a value of pi in there. It goes out there really, really nice. Use it. If you use 3.14 sometimes, then use the pi key. Other times you are going to get values that are going to really be strange. They'll be close, but they won't quite be the same. So if I take a look at these, okay, I've got pi over 6 radians. Now, generally when we do this, we don't write the word radians. You'll just see pi over 6. You'll know that it's going to be in terms of radians because they'll give that to you to begin with. But now what I'm going to do is I'm going to rewrite this as 180 degrees over pi. Okay. So pi cancels with pi, 6 goes into here, and I get 30, so I end up with 30 degrees. Okay. So if I want to do, say, C, I got negative 3 pi over 4, multiply it by 180 over pi. Pi's cancel out, 4 goes into here, and we end up with 45. 3 times 45 is what? Be 135. So this would be negative 135 degrees. Again, the negative can be more or less implied as a direction. Are you going clockwise or are you going counterclockwise? So in this case, when you got the negative on there, this implies that you are going clockwise. Otherwise, all of this stuff is operated in counterclockwise fashion. Okay, a nice little table there, but there's going to be something that we'll be working with later. Finding the distance between two cities. Okay. You guys have played with latitude and longitude before? I was going to say you aren't part of the Earth is flat group, is it? Okay, good. You're spherical type people, right? So when we're looking at these things, you got to understand that the Earth is a sphere. When you're traveling, you're not traveling in a straight line. So finding the distance between two cities. Now, the nice thing is here, these are all on the same longitude. So we consider that the center of the Earth is here. We can identify a degree measure, and we know what the approximate diameter of the Earth is. Granted, it's kind of, we're an oblate spheroid, if I remember correctly, is how it's stated. Kind of squished a little. So, measure the central angle, radius. And let's see, do they identify where the radius is here? Ah, radius, approximately 3,960 miles. Okay, radius of the Earth, miles. Multiply. Area of the sector of the circle. Okay, you guys know how to find the area of a circle? Pi r squared. Okay. Now, if we're given something in radians, we've already seen how we can write radians as a fraction of something. That's all it is. Area of a sector formed by the central angle, so it's going to be r squared theta over 2. Area of a sector. Again, it's just taking the values, dropping them in. Now, is this going to be an opportune time to use decimals? And the answer would be yes. Identifying a fraction when we're talking about area is less intuitive for us. So when I look at this and I see, do the math and I come out 1.05, we're talking in square feet, I got a better idea of what that would be than if I would say 1 5/100 of a square foot. So it makes a little bit more sense to us. Linear speed and angular speed. More wonderful stuff. Okay. Linear speed is defined as follows: S over T. And S is just simply whatever the distance is, miles per hour. Angular speed, however, talks about how fast the angle is opening up. So that would end up being radians over T. How many radians do you travel over a specific amount of time? It's basically the turning rate. Now, angular speed would not be defined at the end. Angular speed would be defined at the shaft. So if you think of a pulley or a gear or the hands of a clock turning around, the angular speed would be identified where the axle is coming out of the back and connected to the hands or to the gear or to the pulley. Or another way to think about it is think about it in terms of your car. Where rubber hits the road, the tire itself is what can be identified as your distance on the outside. That is what will provide you how far you go. That's why for those of you that love putting the big tires on your vehicle and then going down the road with them and thinking that your speedometer is still accurate, not going to happen. Because your speedometer is calibrated for a specific size tire. So your angular speed, that's looking at the shaft. Now your speedometer does not necessarily know what tires that you have on there. So they calibrate it for a specific set of tires. And that way when they use the angular speed, they're able to convert that into linear speed. So if you got a bigger tire on there, your angular speed maintains the same. Your distance is by far quicker, isn't it? And your distance increases, that means your speed is increasing. So last one down here is another one, turning rate. D is equal to RW. It's just another one of these things that you have to have available for. And again, you can write these things down so that you have access to them. I want you to be able to use them, not necessarily memorize them. So you can start building your sheet, copy paste, and start building out your sheet for you to use. Okay, this is radians in unit time. Okay, for W and angular speed, I prefer keeping an eye on this one up here. This one down here for the V, where did that go? See, I don't use it very often, so that means that it's, what is V supposed to be here? V is, oh, relationship between angular and linear speed. I was thinking velocity. That's the difference between them. Okay, linear speed, you guys have dealt with that all. So brings us to here. So I'm going to let you guys get to work on this one.